Welcome to the next section, the next lab discussion video that supports the complete PAC Learn series, Volume 1 of An Introduction to RS-5000. We titled this Universal I/O, and it can be found at approximately pages 72 through 79 of Volume 1 of this Introduction to RS-5000. Now, this particular lab or projects is an exercise to enhance your understanding of the tag database in Logix 5000, or rather in the Logix Engine. So we do this several times through the manual just to emphasize to you that these module-defined tags are instances of a module-defined data structure that supports each different type of I/O module. So we have you create something similar to cement the idea in your understanding of the relationship of these tag structures. Defining universal input-output data structures. In lieu of adding I/O modules, we can do something different and create a virtual I/O structure. This is an alternative to creating I/O type tags using the module-defined data types, which you did in another exercise. Bits in memory are bits in memory. Regardless of what changes their state, what influences them, they're still just bits in memory. So the first thing we're going to do is create a new project. Now, you could do this with an older project and just add these tags, but it may be better if you started clean. Either way, it'll work. So we're going to say new. We'll leave it in L35E. We'll let it be version 20. We'll call it Universal. In the lab, I had you start with an existing project. We just jump right in with a project already created. So it really doesn't matter what you name it, or whether you created a new one or started with an old one. And we want to save it in Learn RS-5000. That's the file that we created to save our programs in. Now, there's already going to be folders in there, files in there, because I don't clear this out every time I start working on this project again. So L35E version 20, we called it Universal. If it makes you feel better, we can call it /IO. Okay? And now you see you have a project. And we don't have any I/O down there. See, we have the compact bus, which is the only I/O bus for the 35E, the 1769 type compact Logix processors. We have a main task, continuous, and within the main task we have a main program with the main routine, ladder style. The little sheet there with a 1 tells you it's the main routine, and program tags. This is all created for you automatically when you create a new project. So we'll collapse some of this back down. We're going to work in data types, and I think we'll collapse down task. So what we had you do is go to user defined and create a new data type and type in the name inputs, and then for the first member just type in an uppercase I. That's all, just an uppercase I. And then for data type, we're going to select a dent. Now we could have just typed in, well, let me cancel and go back here. I could just type in DI, see it shows up NT, and hit enter. And there we have our member I of a dent data type. Okay? Now I had you repeat this procedure, creating a UDT for outputs as an O. So we'll say apply. Okay, we go back to user define, new data type. Go up and give it the name outputs. Uppercase O for member. Data style, DI, hit enter. Apply. Now you have two user-defined data types, inputs and outputs. Now that you have these two new data types added to your group here, remember the predefined and the module defined, it's all underneath data types. So they're all available when you select the data types. So let's go up to controller tags, double click to open it, edit tags, and go to our first blank field, and then we name it. Well, in the manual I showed you a different procedure. We'll do it both ways. IN_01. And then we had you go to type and start typing in inputs. IN, there's your type, hit enter, and you've got it. Now the other way to do this, and I will delete this, another way to do this is to go to controller tags, right click, new tag, type in IN_01, type in IN for inputs, and hit enter. I had you then repeat the procedure, only this time I'm just going to go right here and create it directly in the tag database, and we're going to call it out_02, and we're going to say that the data type is outputs, so we type in OU, there it is, an O gets it, and there we have our two new tags that are instances of inputs and outputs data types. So if we expand, see we have kind of an IO looking tag. Now these aren't the best, but they are similar. In the manual, from here I had you create a rung of Logix. So we'll go up to task, main routine. Of course it opens an empty routine with a incomplete or an incomplete rung ready to go. We're going to add in a true if on and an energize output. So you could basically say this instruction reads whatever memory location you're going to point it at, and say if that memory location is on, this is true, therefore the rung is true, therefore set this bit on in memory. So we're going to do something real clever, and we call this my bit. Then for the OTE, select that, my other bit, because it is two separate bits. And as you probably noticed, that there are E's in front of this rung, meaning that it is an unhappy rung. If you mouse over either one of the tag names, they're not really tag names yet, but they are going to be tag names. Undefined tag, undefined tag. So we need to define the tags. Right click, new, and then we're going to alias it. So instead of base, we select alias, and then the alias for, we're going to drop down and pick input 01. Now this is a word, and here's our 32 bits. So we'll pick bit 0. Create. Now you see it's alias to something that kind of looks like an input. And it really doesn't matter what kind of text you used here, other than it needs to look like it's an input module. Then when I went over to my other bit, new, alias, only this time we're going to alias it to an output. Pick bit 0. Now you have a rung that's happy. Well, it was happy when you defined my bit and my other bit, which we just did, but we didn't just define it as a Boolean. We defined it alias to a bit of a 32-bit dent, which is simulating inputs or simulating outputs. Now we want to download this to the processor. It's always a good procedure to open up RSLinks and look to see that you have the driver configured and that the driver can find the processor. Now, if you notice this red X here, this is for the 1768 ENBT, which is in the passive backplane of the L45 that we've been using. Right now it's turned off, so the red X is there. If we were to turn the processor on, or I should say turn the power supply on, as soon as the Ethernet driver finds that IP address and recognizes it as the ENBT, then that red X would disappear. We're not going to wait for that though. So we're going to leave it turned off because we're not using the L45 for this particular lab project. So we do have RSLinks, so we'll minimize it. Communications, who active, expand the driver, and here is the Ethernet port for the L35E. Remember, that's a daughter card inside of the processor that's built into it. So when we click on that, we expand it to the back plane, and then we go to the actual processor. So you notice over here, this is all grayed out, right? When we select the processor, then this is no longer grayed out. They're active, and we download. And of course, we're going to have that message pop up that always pops up. You should read it at least once so you know what it is when you're just kind of skipping by it. Now, this is a message that comes up on occasion. The controller acknowledged the request for a transition to remote program mode, but it has not completed the transition. You cannot download until the transition completes. In order to download, it has to be in the remote program mode. It didn't do it fast enough, so we got this message. So we click OK, we click download again. Now I could have went to the key switch and put it in the remote program mode. Download, now it's downloading. I'm not exactly sure of all the details of why it doesn't do it fast enough, but nonetheless the message comes up at least 1 out of 20 times that I go to download, so I thought it was worth mentioning. Just click OK and repeat the process. Okay, now we're in the remote program mode. We'll put it in the run mode, remote run. So now this single rung of logic is executing. Of course, it's executing thousands of times a second simply because that is all that's in there to execute. If we go to the main task, right click, go down to properties, go to program, phase, schedule, monitor. I'm clicking through these because we went through these earlier when we were offline. Now we're online. So remember I told you there's not much to look at when you're offline. Well, now we're online, so it's monitoring. The maximum scan time, and I assume that was the first scan, was 1.72 milliseconds. So basically a little less than 2 thousandths of a second. But the last scan, as you're looking there, you can see it varies between 60 and 70 millionths of a second. Or, because remember this is milliseconds, so if you move the decimal place over to here, then that's millionths of a second. So basically this is executing about 8 times per millisecond, or 8,000 times a second. Okay, if I reset, I get something a little less than what I had for the maximum before. So there's something going on in the background that occasionally it takes a little longer to execute this task. So let's close that and then go to the main program, right click. You can't see it, it's off the bottom of the screen, but I clicked on properties, we go to monitor. Now you see its execution time is in microseconds. That's not us. That's microseconds. So you can see that the standard execution time for that main routine is 18 microseconds. So you see there's a lot of other overhead involved that takes place besides the execution of that single rung of logic. And that single rung of logic is not actually taking 18 microseconds. That's what it's taking to run the program. So I'll click cancel. If we go to main routine and go to properties, there is no monitor for that particular routine. Okay, what I wanted to show you was that you created these tags, and these tags, even though they're controller tags, they are not I/O. You see that the data type is, you see no I/O data types here. We have no I/O here in our project. If I right click on that bit, so what I'm doing is saying I want to toggle that bit on. When that bit toggles on, then the logic, when it executes, turns this bit on. If I look at controller tags, go to monitor tags, you see they're both on. If I turn this bit off here by actually running the cursor through it to highlighting and hitting 0, when I hit enter, you see my other bit turned off. The whole purpose of this little short lab was to emphasize to you that these are just bits in memory, even if they're aliased to something that looks like I/O. Because there is a way that you can actually use the I/O data types under module define without actually having any I/O modules. You basically create the I/O modules, then you delete them, then you use the data types that are exposed. The problem is that if you try to export it to another location, in other words, you export it to a library or something, and when you pull it back in, it's going to clean it all up and it's going to remove those I/O data types, and you're going to lose your structure. So you're better off not using module defined tags when you really don't have I/O modules there. We're in the run mode. If I go to this bit and toggle it, it actually did turn on, but it turned back off so fast that you couldn't see it. If I go to this bit, toggle it on, then put this in the program mode, you see it still looks the same. That's because the last thing that this bit heard was, from this rung of logic, you're on. Stand up, you're on. If I toggle this bit back off, notice that that one stays on because we're not executing this rung of logic. So this rung of logic right now is not being executed and controlling this bit. If I turn it back on, if I put it back in the run mode, so watch, this is off. This is true if on instruction, but the bit is off, so the rung is false. So when I put this back into the run mode, watch my other bit, the OTE there, when I click on yes. First time it executes, it turns it off. Okay, you just executed a rung of logic without the benefit of I/O module. If you have watched the other lectures, then you understand that a bit in memory is a bit in memory. The logic does not care who turned it on or turned it off. It's just a memory location that is being addressed by instructions in the program. So this was a nice simple exercise in creating tag structures, executing logic against them, but there are not actual input and output field devices connected electrically to these memory locations. Thank you for watching this lab project discussion video on creating and using universal I/O.